Hello, please confirm that you can hear me. Yeah, I think it's working now. Hello, please confirm that you can hear me. All right, that's great. Okay, it's nice to see you all. Welcome back. Today is just about going over what we went through the last time, and hopefully, I'll be able to explain better now. And for those of you that were not there, this is like an opportunity for you to catch up and also register your attendance. Um, Let me start by saying the live chat is how we communicate. As I continue to speak and teach, if you have any question, any comments, please drop it in the live chat. I can see the live chat directly. So that's how we're going to communicate with each other. So let's get started. Today we are talking about basic electronics for solar engineer. This is like the most basic um, theoretical part of the training. I would, I strongly advise you understand it very well because what you're going to learn right now is like the building block for every other thing that comes afterwards. So, before I continue, please confirm that you can hear me clearly, not just that you can just hear me. So I'll know if I need to speak louder. All right. So okay, that's great. Thank you, Fire Me. So sometimes within the training, I'm going to send the attendance link to the live chat, so you can quickly register your attendance. Because once the live stream ends, you might not be able to have access to it again. So let's begin. Before we continue, um, give me a moment. Yeah. So to one of basic electronics as concerned with a solar engineer. First, let's deal with the main terms. The main terms we'll be talking about today are one. Let's not start with this guy. Let's start with the most basic one of them. We'll be talking about the charge. Um, okay. Then after that, we'll talk about the current. And we'll talk about the voltage. Then we'll talk about the power. We talk about energy. And lastly, we talk about resistance. Good. These are the main terms we'll be talking about. But to help you understand it better, I will be explaining it in a. I'll be using a water tank analogy. Tried this the last time. Hopefully, I'm able to explain it well this time. So imagine the big storage tank, the one that is usually on top of your house, where water is stored and supplied to the rest of the house. Just imagine a big storage tank. So imagine this is a storage tank containing water. Now, I'm trying to relate this storage tank to a battery. I want you to explain what all these things mean as related to a battery. In an attempt to do that, I'm comparing it to a water tank. So I'm going to compare the both of them and then explain what each term means like in a manner of speaking. So this is a storage tank containing water. Let's take charge. Charge is what is stored inside a battery. So compared to a storage tank, charge will be the water inside the tank. So a charge is what is stored inside your battery. Uh, a charge is not really a physical component that you can just open the battery and find. It is a state, maybe electrons, hole, the flow, Examples, for example, uh, there's this concept called valence electron when you were in school, and then if there is no valence electrons, then electricity cannot flow because there are no negative and positive charge carriers. So a charge is what is stored inside the battery. Now let's move on. When I open this tank, water flows out of it. The flow of charge out of a battery is called current. Now, if I open this tank midway, less water will flow as if I open it fully. So we can also control the amount of charge we get, and that value is represented by the current. Let me write it in mathematical terms. Let's say current is represented by I. So I is equals to Q over T. What this tells us is that current can be defined as the rate of flow of charge. So charge is coming out of the battery. The rate at which it's coming out, maybe we're getting 10, I think charge is coulombs, right? Uh, Maybe we're getting 10 coulombs per um, per per second, or we're getting 20. That is defined by the value of current. For example, let's say we have 20 amps. 20 amps means we're getting if we have 20 amps and we compare it to 10 amps, means we're getting 2 times more charge out of the battery. Of course, current depends on the load, right? Um, let's say you plug a phone to a battery, you will get less current as if you were to plug a washing machine to the battery. It's a matter of demand and supply. Okay, the load needs so amount of current, and then the battery supplies that current to it. Next is voltage. Compared to this water system, voltage will be the level of water in the tank. If the tank is fully filled and you open your tap, for example, let's say at home in your house now, your maybe your landlord has just pumped water and the water is like the tank is full, and then you open the tap in your room, you realize that the pressure of water coming from that is far more than when maybe a lot of people have used this and the water is almost out. So you'll be able to tell the difference that, oh, I'm not getting as much water and because there is no much water in the tank. So that is the analogy there. Now, that same logic can be applied to a battery. The level of charge in the battery is what we call voltage, right? I know this is kind of not what you are used to. You are used to understanding this concept by definition. Just say voltage is potential difference, and current is how do you even define current when we're in secondary school, right? Our goal at Imole is to build a professional solar engineer. We cannot make you a professional solar engineer if you don't understand the concept. So I want you to understand the concept to the core because that is the foundation for every other thing you're going to learn in this training. So voltage is the level of charge. Now, depending on the voltage, so from what I just explained, I said of water in the tank. It will control the flow, the pressure at which comes out. That means depending on the voltage of the battery, that can affect the current we get from it. I hope I'm making sense. So yeah. Now, how do we know when this tank is low and when it's high? When there is not a lot of water in it, we say the tank is almost finished, and when there is a lot, we say the tank is full. That same logic can be applied to a battery. When there is not a lot of voltage, when the voltage value, because voltage is not something that's inside the battery, when the voltage value of a battery is low, we say the battery is low, and then when the voltage reaches a particular value, we say it is high. For example, the battery we usually use in solar engineering, the lead acid battery, has a low voltage level of 11 and a high voltage level of 14. So lithium have 12.6 for their high and the low is 10.5. So depending on the battery, you have a high level and a low level voltage. Let's move to power. Power is what is actually stored in the battery. Like power is a measure of what is stored in the battery. I mean, we said earlier that um, voltage is the level of charge in the battery, and current is the flow of that charge out of the battery. Now, if we combine those two terms together, we can we can represent them by one term, and that term is called power. Power is a measure of what is in the battery. Now, the power of a battery differs from one another. We can have a lead acid battery and a lithium ion battery, and their power level might be different because um, we know that current is a function of voltage, um, and then there has to be something that relates them together. If I say current is a function of voltage, um, the higher the voltage, the more the current. The higher the water in the tank, the more flow, the more pressure of water you're going to get. So there has to be a formula that relates them, that helps us exactly calculate how much current we can get given a particular value of voltage. And I'm pretty sure you know that formula. It's a very popular formula. It's called Ohm's law. According to George Ohms, okay, this is out. According to George Ohms, it says V equals to IR. Side note, these videos are going to be made more professionally and posted to the channel. When it's available, I'll let you know. V equals to IR. This is the formula Ohms gave us. According to this, it says we can calculate the voltage given a current once we know the resistance. So remember I said earlier that power differs. I said power is voltage and current combined. Let me just write that for reference. P equals to IV. This is the formula for power. So when I say power equals to current times voltage, and I say power differs depending on the battery, then what makes it differ? I mean, look at the two formula. The one thing that differentiates each battery from one another is this, the resistance. So depending on the resistance, we can get different power values. I hope I'm making sense. Let's continue. Um, okay, before we continue, I want you to understand proportionality. When you were in school, you were probably taught proportionality. Something is directly proportional to something, and something is inversely proportional to another thing. But in our training, you need to really understand what that means. When I say A is directly proportional to B, let me write that down. When I say A is directly proportional to B, what this means is that if A increases, B will also increase. Also, mathematically speaking, we can say A equals to KB, K, where K is a constant. So, what if I say A is inversely proportional to B? This means that if A increases, B will decrease. Mathematically speaking, we can say A equals to K over B, or we can say K equals to AB. Now, how do we apply this to our field? Remember Ohm's law, the formula we talked about recently, where we say V equals to IR. And I told you that the one thing that's constant here is resistance. This tells us that V is directly proportional to I, which means the higher V is, the higher I is going to be, provided that R remains constant. Now, we're getting to the part, we're getting to the fun part. Oh yeah, before I continue, I've talked about power. What is energy? Energy is the power used over time. That's just what energy is. I said power is a measure of the current and voltage, probably a measure of stored energy. So I said power is a measure of the current and voltage. What is energy? Energy is the power used over time. So when I say I used 10 watts, um, I used 10 watts in 10 seconds. Then my power is 100 joules. We'll get to the calculation shortly. What is resistance? Resistance is opposition to the flow of charge. For example, um, using our water tank analogy, you open the tank and then in the pipes, there are like a lot of debris in the pipes, stones, and so on and so forth. Once you open the pipe, you won't get as much pressure as you want because of those debris. Of course, there are in an ideal situation, there are no debris in a water pipe. But then, assuming they are, those debris will represent resistance. Now, let's move on. Let's talk about the formula so we can understand these things better. Charge, well, is represented by Q. I'm not going to write the formula for charge on the board because it's not related to what we're doing. Let's move to the next one. Current. So current is I equals Q over T, which is what I've written. It's simply the rate of flow of charge. Yeah, put it that way. The same way you measure speed for traveling, the speed of charge is current. Voltage, yes. We have talked about what voltage is, and we have related it to Ohm's law, V equals IR. Power, power. Okay, let's talk about power. Yeah, we've written that power is P equals to IV, which is the multiplication of current and voltage. Um, Energy. What's the formula for energy? Energy is simply power times time. It's the multiplication of power and time. And if we are to substitute IV for P, it will become IVT. All right. Um, let's talk about resistance. Very, very important. Now, this is the one I want you to pay utmost attention to, the formula for resistance. The formula for resistance equals to R equals PL over A, where this is called resistivity. L is length, A is cross-sectional area. What cross-sectional area means is if I have this marker and I split it open, the area of the top here is what we call cross-sectional area. And yeah. Now, according to the proportionality we did earlier, then what would this formula mean? What it will mean is that R is directly proportional to resistivity, provided every writing is constant. R is directly proportional to length, and R is inversely proportional to cross-sectional area. You need to understand this very well for the sake of wiring. In solar engineering, there's the panel, the wire, the charge, the battery, the inverter. Those are the five essential parts of the solar engineer of a solar setup. The wire is perhaps the most important part because that is where most people get it wrong and then eventually have complaints and issues with their customers. Now, when choosing your wire, this formula is very, very important. Let's talk about the first one. R is directly proportional to resistivity. Resistivity here is an intrinsic property of an element. When I say an element, I mean a material. When you cut open, there are different kinds of material used for wiring. We have the copper, we have aluminium, we have iron. I think we even use zinc, and so on and so forth. And then each of these material have their own resistivity value. It's a constant value. It's an intrinsic property of the element, except in situation where you have an alloy and two metals have been mixed together. In such a case, you will have a varying resistivity. Now, what this formula tells us is that we want to use we should choose to use the material with the lowest resistivity. And I sent so the first assignment is for you to find um, all the materials, metallic materials used for wiring, and their resistivity, and also tell me which one of them is best for wiring and why. Next, we have resistance is directly proportional to length. Resistance being directly proportional to length. What this tells us is that if you have a wire this long, if you have a wire this long, you will get less resistance than if the wire is this long, because um, the longer the wire, the more resistance there will be to the flow of current. And you should know that this resistance is actually a waste of energy. It can manifest itself in form of heat. That's why you see wires getting hot sometimes, and this can cause fire and power else. Um, yes. So let's say we went to we installed solar in a bungalow, and we use 10 meters, 10-meter length of cable. And then the person we installed for moved to a 5-story building. And then we just say, oh, it's simple. I will just buy like 5 times, that's 50 meters length of cable and just use it for the person. It won't work exactly the same way. You will probably lose about 20% power, even more. The reason why it won't work is because you have increased the length of the wire. Therefore, there is more resistance. What you should do is this third one. When we talk about this third one, you'll be able to know what to do. Lastly, R is inversely proportional to area, which tells us that the larger the area, the less the resistance. The smaller the area, the more the resistance. When I say area, I mean like thickness of the wire. So if I use a 1 mm wire compared to me using a 16 mm wire, a 16 mm wire will offer less resistance compared to the 1 mm wire. So when the person move from a bungalow to a 5-story building, what you should do is to increase the thickness of the wire. Of course, you should know exactly by how much you need to increase it. We're going to cover that later on in the section concerning wires. Yes, I think that's concludes today's lesson. It's just a recap of what we did last time. Also, one more assignment. You should what's it called now? Yeah, you should list the different sizes of wires available. So that's another assignment. I've sent the assignment link to the group. Make sure you answer the assignment and let me now send you the attendance link. All right, so I've sent the attendance link to the group. Make sure you fill it on time. It will close very soon. So now that I know that, we have like 3 minutes remaining. If you have any question, send it um, to the live chat. Those of you that have done the assignment before, you don't need to do it again. So if you have any question, send it to the live chat so I address them. Now, while we are here, please make sure you subscribe to our social media channels. I'm going to send it to the group again. Subscribe to it, and I advise you to engage online. Right, as a solar engineer, most of your customers are people you have never met before, and these people are not just going to miraculously find you. They don't know who you are. They don't know what you do. So the best way to prepare for future is to start engaging right now. And to do that, we advise that you follow us, send posts. Yeah, we have an X page, I think. Send post, create posts online, send pictures of what you do, screenshots. By the way, you're free to use any of our videos, and maybe record yourself explaining all this voltage, charge, and everything. Tell people you have started studying at Imole Solar. Engage with us, and our PR team are actually quite welcoming of this. For people that engage actively, you're going to like award an extra 10%. And in case eventually your grade is not up to 70% by the end, that extra 10% can help you graduate. So um, the attendance should be accepting response. Okay, let me open it. All right, I've opened the attendance, so um, you should be able to fill it now. Also, please, and please make sure you are using your matric number. If you don't have a matric number, let me know. Message me privately. You need to be using your matric number. That's the only way you'll be graded, and not your school matric number, the Imole matric number sent to the group. So we have 1 minute remaining. If you have any question, this is the last chance to send it. All right. I would like to say hello to David, um, Mohammed, Fayomi, Matthew, Oluwadare, Edwin, Adeoluwa, and Salami, and every other person, Mujib, Abdulkabi, and Glory, and every other person in the live stream. Thank you for joining, and I hope to see you in the next one. The next one is on Sunday. Please be punctual and pay attention. Good night.